introduction, and thank you for coming to my talk. So today I'm going to talk about practical of Crosscap CFT and some emergent physical features in it. So this talk is made based on like later shortly. So during this talk, I think my goal today is to convince you that there is a correspondence between two-dimensional homology theory defined on non-quantum magnetic fields, and also 3D Einstein gravity with two-dimensional Zixia and HEP-QIS. So this sounds complicated, right? Why should we even care about this random stuff? So motivation actually comes from the Zixia holography. We know that holography has played a very central role in our understanding of quantum gravity, and especially the HEP-QIS oneness is the most successful example. In the HEP-QIS oneness, it states an equivalence between quantum gravity in d+1 dimensional antithesis spacetime and also a d-dimensional quantum field theory living on its central boundary. On the other hand, our universe seems to be better described by the Zixia spacetime, so there are many attempts on constructions of the Zixia holography. But compared to HEP-CFT, the Zixia holography is often way much more exotic. So in HEP-CFT, there are many good properties we take for granted. For example, we have a canonically defined time direction. For each time slice, we can define a Hilbert space. And the CFT appearing in HEP-CFT is just a standard CFT, so it has locality. It also has unitarity. So in order to find some the Zixia holography, we have several different approaches. One such approach is to just do some kind of calculation from HEP-CFT. Then you will get a correspondence between DS and CFT. So in this context, the continuation is a weird thing where for the CFT side, you don't have a time direction anymore, and you don't really know how to associate the Hilbert space to the CFT. Also, the CFT appearing here is not a unitary CFT. It does seem to be local, though. There are also other kinds of the Zixia holography. For example, DS correspondence and various kinds of static patch holography. So in those cases, what you do is that you will start from a higher dimensional Zixia spacetime, and you specify a time codimension 1 surface in the Zixia spacetime, and you associate a quantum system on that codimension 1 time surface. So by construction, it has a canonically defined time direction, and you can also accordingly associate Hilbert space to each time slice. And it also seems to have unitarity, but in all those cases, if you think about the higher dimensional counterpart, it does not have locality. So for example, you can think about, static patch holography. You can compute the decay of OTOC, or you can also compute holographic entanglement entropy. You will find they have some very notable feature.
Can you comment on this locality in DSCFT, particularly in the evidences?
Oh, sorry. So here I put this a check here, but that's something we don't really know. So in order for it to really have a CFT, it should satisfy modular bootstrap equation, blah blah blah. But we don't really know whether that's true or not. It just seems okay, but yeah, we don't really know. As physicists, we are kind of greedy, right? If possible, we want all three of them. We want a time direction, we want locality, and we also want unitarity. So what I want to do here is that instead of the Zixia itself, let's think about some ADS 3 spacetime with the two-dimensional Zixia ends up work. But why? Why should I think about something like this? So there's a very simple reason. The very simple reason is that because we are very familiar with HEP-CFT correspondence. And we know that the CFT2 corresponding to APS3 has time, locality, and unitarity. So like even though you put something like inside this kind of space-time, the whole thing should just be described by a sector of such a good theory. And there's a slightly deeper reason. A slightly deeper reason is that in recent years, we kind of know that holography, which is related to APS3 space-time with APS2 and equilibrium, turns out to be very useful in understanding quantum gravity in two-dimensional APS space-time by something called double holography. So here's a sketch of what we mean by a double holography. We can start by thinking a CFT, which is defined on a manifold with a boundary. So here we call that manifold sigma, and the boundary is denoted as partial sigma. Then we can think about two different kinds of holography associated to this picture. The first thing we can do is that we just ignore this sigma part and only look at the theory on the partial sigma. And we apply the APS-CFT correspondence on this partial sigma. So, for example, if sigma is two-dimensional, then partial sigma is one dimension. Then that one-dimensional stuff can be related to a two-dimensional APS, which is denoted here as cube. So that's one way to realize a holography. And there's another way. Another way is that you just regard the whole stuff as a part of two-dimensional CFT. So of course, it has a three-dimensional APS counterpart. And in that three-dimensional APS counterpart, you should have a sector which describes this boundary of the CFT. And that turns out to be like an APS2 and of equilibrium in this case. So it's a kind of triality. This triality is not like very precise, but it has something which is a boundary CFT, which is a BCFT. And this BCFT is totally well-defined, and it is really complete. So no matter what happens in this kind of triality, we can always go to a really complete picture to kind of understand what's actually happening in all these pictures. Also, we also have a bulk picture, which is APS3, that turns out to be classical and very easy to analyze. Like this picture, I will call it an intermediate picture. This is not precise at all, because when I introduced this one, I said, okay, just ignore the sigma and look at partial sigma and then do something. But we don't really know how to actually cut down that copy, so that's not so precise. But it turns out this picture can serve as an amplifier of quantum effects of gravity. So it is very useful for guessing things. Here is an example. In this paper, the authors...
Can you clarify in what sense intermediate picture is not precise? I think that the Randall-Soder localization is what makes it precise. We know what it is. It's just not like purely massless gravity.
Yeah. So like there are many senses why this is not precise. So from the Koch-Randall point of view, we know that like the intermediate picture is a low-dimensional effective theory. But if we go to very high temperature, not high temperature, like some very high energy, then on the BCF side, we know what happens. On the bulk side, we kind of know what happens. But we, like the effective field theory on this intermediate picture, it loses like effectiveness. That's.
Sorry, in what sense the intermediate picture loses it, but not the higher dimensional? If you go to very high energies, all effective theories break down, right?
Oh, like the effective field theory breaks down, but like at the leading order, we know classically what happens like in bulk. Maybe let me take another way to explain why it's like just effective. As I said, like in this picture, like this part and this part, they are coupling through like one dimension one interface. But here, like the degrees of freedom localized on this boundary, like all of them are in some way coupled to the sigma. So you don't really know how to like decompose those coupling, which is organized in this way. So that's what I mean by not so precise. But I mean, if it's like more precise, it's better. So yeah. But thank you for the comments. But one thing I want to say is that it's very useful for guessing this. So here's an example. So in this paper, the authors argue that if you think about entanglement entropy in PCFT, which is a totally well-defined thing, that's highly related to some dynamic computation in the block, which can be further interpreted as an Allen formula in the intermediate picture. While this one is not precise, you can guess by thinking about this, and then it is like later shown by using the gravitational coupling tool. So, while the reason why it is like so useful, I think is because it has a UV complete stuff like in this triality. So no matter what happens, you can always go to the UV complete picture and then figure out what's actually happening, like in the whole stuff. So let us schematically write the things down in this way. Then what we would like to understand is that instead of the ABS2 tensor flow, we want a DS2 tensor flow. Then presumably that can be used to understand some two-dimensional DS quantum gravity, which is coupled to non-gravitational CFT. However, we don't really know what's the UV complete description of this kind of stuff. It's very different from this side. On this side is like BCFT, but on that side, people didn't really know what's the thing. So that comes to our goal today, where I would like to argue that the CFT dual, the UV complete CFT dual, is actually some two-dimensional confound field theory, which is defined on non-orbital manifolds. So from now, I'm not going to explain why it was hard to find a UV complete CFT dual for DS2 and alpha orbits. Instead, I will just start from 2D CFT on non-orbital manifolds and then try to get the lower description from that. So far, is there any questions? Okay. Sure. Let's then think about non-orbital manifolds. So the most simple two-dimensional non-orbital manifolds is something called a real projective plane. So the way to define a real projective plane is that you start from a truth sphere and then you impose antipolar amplification to other points on this truth sphere. There's an alternative way to depict this picture, where you can just start from a hemisphere and then you identify antipolar points on the boundary of the hemisphere. And that kind of thing is called a crosscap. It is known that any two-dimensional non-orbital manifold can be realized by inserting crosscaps to ornithable ones. So in that sense, we will call such a CFT a crosscap CFT. I will use XCFT to denote crosscap CFT. Maybe CCFT is a better name, but yeah, I will use this. Okay, so let's think about holography associated to XCFT. There's actually a topological obstruction for constructing the gravity dual for an XCFT. There's a very simple reason. So when we are finding a holographic dual, we're looking for bulk geometry. But it is known in commodism theory that there does not exist any 3D manifold such that the boundary of the 3D manifold is RP2. So there are also papers works on holographic crosscaps, but they have not mentioned this. I will explain what they did later. In order to make it more clear, let us think about a specific example. So let us start from the CFT, which is defined on two sphere. And then we all know the gravity dual is just a UV ABS3 whose metric can be written in this way. If we use the GPT Witten dictionary, then what we are actually doing is that we give the boundary geometry and we solve the Bloch-Einstein equation to get the gravity zone. So here I would like to write down the Bloch action, which is just an Einstein-Hilbert action with the Gibbons-Hawking term on the symplectic boundary. Okay, let us then very naively squash this two-sphere into an RP2. Then, of course, there is a magnification on the two-sphere in order to get this RP2. Then one thing you can guess is that maybe you can extend this Z2 amplification deep in the Bloch. But by doing that, you will get a singularity here at the very center of the Bloch. So you might think, well, there's singularity, but maybe we can include higher derivative correction or just allow complex matrix to resolve this singularity. But that's actually not doable because, as I explained before, this singularity comes from Cobordism topological obstruction. So in previous literature, what they did is that they just leave the singularity there and then try to think about correlators and something like that. But in order to really apply the GPP-Witten dictionary, you need to resolve the singularity. Because
so previous works assume that's the right saddle?
Previously, they just leave the singularity there, and they said, okay, it's not a saddle point, but it has the correct symmetry, so let us just think about computing correlators in this background. It's something like that. But yeah, but it's not a solution of the Einstein equation. Okay, so what we would like to do is very simple. We would like to just add an additional term to the Einstein-Hilbert action. So here, this term is something we call an end-of-Waldron, where we put some tension on this term, and we impose the Neumann boundary condition on this new section of the spacetime. So there's a motivation from a 10-dimensional point of view. Although we're only looking at bottom-up construction in area 3 and CFT2, we can think about what if we have a top-down constructed 2-dimensional holographic CFT. Then in that case, what we are actually doing is that we're looking for 10-dimensional geometry whose symplectic boundary is RP2 times some 7-dimensional compact spacetime. So we have already explained that RP2 cannot shrink in the Bloch because of Cobordism. So it must be the 7-dimensional compact spacetime which shrinks in the Bloch. And then if you take that point of view, after doing the dimensional reduction, that would just be an end-of-Waldron from the 3D point of view.
When you have this internal manifold, can't you resolve the singularity by just accompanying the antipodal map with some involution in the internal manifold, like a rotation, or a rotation without fixed points on the sphere? There'll be smooth even if there's no smooth manifold with RP2 boundary, once you have the internal space, then there are smooth manifolds.
So there's no fixed point?
Yeah, so you can, if you have an all-dimensional sphere, then even a rotation by pi around some typically has no fixed points.
So I think that corresponds to maybe inserting some orienting fault at the very center of the 10-dimensional spacetime, right? Probably.
No, there'd be a smooth spacetime. It's smooth with a certain amount, yeah. Maybe, yeah. Perhaps it's hard to keep the right boundary conditions in the internal space.
Yeah, I think that's
What are you imagining doing here?
You can make a smooth manifold by you do the antipodal map, you also do some involution in the internal space.
Yeah.
So like a rotation halfway around a circle.
Yeah.
And then I'm just wondering if this is the same picture, but
Right, sorry.
Yeah, I think that picture also works, but that should also lie in this class because no matter what happens, it's a smooth saddle point. there should be some like some direction on the boundary which smoothly caps off like in a block. Like in the usual ADS3, it's just like the boundary has to it like a smoothation like in a block. If it's BTC graph, it's
But you can have a case where the
boundary has to have trivial homology, right? Like this is not. It's the only boundary.
right, but it doesn't have to. Like an example is a spatial slice with this R2 geom, which is like so there the boundary has it only has to have trivial Z2 homology. It doesn't have to have trivial Z homology anymore. It's not very good.
Oh yeah, now I got your point. So in order to have that, you need actually two crosscaps. So I will actually discuss about the geometry like later. But here I only have like one crosscap on board, so that's actually not doable. Like,
Yes.
Yeah. That's at least in two crosscaps. So one. Yeah. So one thing we need for this action is that we need the action to not change anything we already know. So actually, this modification does not change anything of the block variables that we define our origin methods. So let's then look at what is changed for our case. So again, like think about a CFT defined on RP2. Then after introducing the new term, the most dominant solution in this case is like a Euclidean ADS3 with an end-of Lagrange sitting at the center of the block. So if you remember that we introduced a tension term on the end-of Lagrange, the tension term and the location of the end-of Lagrange is actually related by this. The physical region in this picture is the eta greater than eta star region. Roughly speaking, what happens in this picture is that the singularity is just removed by this end-of Lagrange. From topological point of view, what happens is that after introducing this end-of Lagrange, the boundary of the whole 3D block turns out to be a union of two RB2 in this case. And that is allowable like in robotics. Okay, so yeah, sure.
Sorry, will you comment later about the let's say, intermediate feature in this case?
I'm actually not gonna comment on the intermediate picture.
Okay, because I think that in this case, gradient localization just doesn't work, right?
Sorry?
Gradient localization in this case just doesn't work. It's like if you're looking to a DS brain for which gradient localization works, but from the inside out.
Yeah, so
you don't have like an ADS potential that supports gradient.
yeah, exactly. Okay, so I'm not going to comment later, but I can comment here. So what happens in this case is that although the graviton does not localize on this rim, this kind of setup is actually the setup which is identical to the random sampling 1 model. In the random sampling 1 model, you have two end-of Lagranges. You have a negative one, a negative tension one, and you have a positive tension one. And it is thought that our universe is living on the negative tension one, where the graviton actually does not localize. So it's more like that kind of scenario, if we think about the remote counterpart. So it does not have a localized graviton, but that's okay because that's also what happens in the random sampling 1
Well,
case.
sorry, why is that?
Sorry, like in the random sampling 1 case, it is thought that our universe is living on the negative tension ring, where the graviton does not localize. But it's because the graviton does not localize that explains why the gravity in our universe is so weak. So the fact that the graviton does not localize explains the hierarchy problem in that setup. But I'm not gonna discuss about that. Probably in this. We can chat about that later. Okay, so now let's just do some specific check to match the two sides. So let's just firstly check the symmetry, right? So on the XCFT side, the original symmetry coming from the global conformal group is SO31, where like there are 3 isometries coming from the 2-sphere and there are other three special photonic transformations. So here, after doing the Z2 quotient, where you identify the antipolar points, then of course the three isometries will survive. However, the three special compound transformations, they does not map gray circles to gray circles, so they are broken. And the whole compound symmetry is broken into SO3. Then on the ADS side, it manifests this SO3 because you essentially introduce a center to the ADS3 in the bottom. Let us then think about the partition function on the two sides. So on the CFT side, the RP2 partition function can be schematically written as an inner product between a CFT ground state, which is prepared by this lower half hemisphere, and a crosscap state, which is a kind of boundary condition imposed on this gray circle. And in terms of, there are several generators, the crosscap states satisfy all those constraints. There are some there's some related quantities to the RB2 partition function. Well, sometimes we use a P function to call the RB2 partition function, and we call the logarithmic of the P function as the crosscap entropy. So on the ADS side, we can also compute the RB2 partition function as a function of the tension of the ends of the equilibrium, and the crosscap entropy is related to the tension that this way. This is not a consistent track. This is the development of the dictionary, and we will later do the consistent track for what we develop here. Then we can compute the one-point function on the two sides, and it also turns out to be the same. Okay, let us then think about a slightly more complicated case to do the consistent check. So before we talked about RP2, and RP2 is a manifold with only one crosscap. Then the next complicated example is a Klein bottle where you have two crosscaps. So here I depicted a sketch of the definition of Klein bottle. So usually we use this picture to define a Klein bottle where you identify like this boundary and this boundary. And you identify this boundary and this boundary with the parity twist. Then by doing copy and paste of this definition of Klein bottle, you can get another definition of the Klein bottle where you start from a cylinder and you introduce two crosscaps on the cylinder. Then if we look at the very right side of this path integral, then you can easily find that this Klein bottle partition function can be written as an inner product between two crosscap states. On the other hand, if you look at the leftmost figure, then you can find the Klein bottle partition function can be written as something like this, where omega is an inverted parity operator. We can very easily solve two limits of this partition function. We can take the beta goes to infinity limit and beta goes to zero limit, where we get some very universal expression of the partition function. And this can be regarded as the Klein bottle version of Cardi formula. Then we can.
It's non-universal. P depends on the CFT equation, does it?
Oh, sorry. P. Yeah. Sorry. Like it universally has this form, where P is not. It's not universal. Yeah. Sorry. Yeah. I mean. Yeah. Exactly. So then we can solve like our equation of motion to find the box saddle points. So in this case, you can find two competing saddle points in the bottom. The first one has this metric, and there's no ends of equilibriums in this metric, and no singularity, just as we mentioned. This is exactly the geometry which Harry just mentioned. And as I just explained, here you need actually two crosscaps, and once you have two crosscaps, there's no cubalism obstruction for having a bulk. On the other hand, you have like another saddle point where you have another metric, and 2 disconnected keys of the ends of the hologram. And you can also compute the action coming from that set of points. Then the whole holographic partition function is given by a computation between those 2 saddle points, where there's a Hawking page transition at a specific temperature. And if you look at the 2 limits at low temperature and high temperature, they matches the universal CFT result precisely. So this is a consistent check. Is there any questions so far? Okay, so far we have described a correspondence in the Euclidean sense for ADS with some ends of hologram and Crosscap CFT. Now I would like to explain how is the two-dimensional DS described in this framework. So in order to do that, let us go back to our gravitational bulk dual to the RB2 CFT. Here I wrote down the metric and location of the end of hologram. Let us do a coordinate transformation to change it to another coordinate. And in the new coordinate, the boundary dual is naturally identified as a Z2 quotient of an infinite cylinder. Then let us use this coordinate and then take the identification from Euclidean time tau to Lorentzian time t. You can say in the new Lorentzian time direction, the ends of hologram shrinks and bounces in the time direction, and the intrinsic geometry of this end of hologram is locally ds2. So here, there's actually also an identification on in this geometry, and it is interesting to find that it naturally introduces an identification between t to t plus 2 pi. What that means is that the ADS appearing here is actually exactly just global ADS theory, which is not the universal cover we usually think. Is it clear so far? Okay. Okay, now let us write it in the Hilbert space language. So if we look at the Euclidean setup we're looking at, if we insert any local operator or non-local operator on a fixed time tau prime, then what's happening? Sorry for that. Then what we are actually computing is a local operator which is sandwiched by the ground state of the CFT and the crosscap state of the CFT. Because this is true for any operator we insert in this path integral, so what happens is that given a fixed Euclidean time slice, then that fixed Euclidean time slice is described by this kind of matrix, which we would like to call a transition matrix because it has a different Bragg cat. So if we take the tau goes to IT continuation, we directly get the Lorentzian counterpart of the picture we depicted here. So what happens in this case is that you have a time evolved crosscap state, and you have a time evolved ground state, and this combination gives you a description of this DS2 ends of hologram. Let us look at some special time slices to do the consistent check between the ADS and the CFT side. Of course, the most simple time slice is the t equal to 0 time slice, which is just at the center of this picture. So at t equal to 0, our CFT dual is given by a matrix, which is a combination between the crosscap state and the ground state. And as we have already mentioned, this crosscap state satisfy this kind of constraint. So in terms of global conformal symmetry, the transition matrix at t equal to 0, it's invariant under these three global conformal generators. Because like this 0 trivially satisfy all the conformal symmetry, and C satisfy 3 of them, so the combination also satisfy the 3 of them. So if you look at these three, they form SL2R, and this SL2R is exactly the symmetry of the t equal to 0 time slice here in the block. That is like one rotation here and 2 boosts like here. Sorry for my bad gesture, but yeah, you can check the symmetry matches in this t equal to 0 slice. Let us then look at a slightly non-trivial time slice, where we take t equals to pi over 2, and t equals to pi over 2 is this time slice, where the ds ends of logarithm touches the symptom boundary, and it's very singular. Then, according to our proposal, the CFT dual is given by a combination between a time evolved crosscap state and a time evolved ground state. You can explicitly check from Virasov algebra that this time evolved crosscap state satisfy another set of constants. Again, this 0 is not changed under the time evolution, so the whole combination satisfy these 3 symmetries. And these 3 symmetries, again, form another SL2R. And this SL2R is another set of SL2R, but you can check that they match the bulk symmetry at t equal to pi over 2, where you have 2 translations on this direction, on this direction, and the rotation on this direction.
So sorry, the end of the world braid is coming right out to the boundary here?
What?
The end of the world braid is literally hitting the boundary here.
It's like it's like literally hitting the boundary.
There should be some signature in the boundary that's happening, right? So
I would explain what that signature is. So yeah.
I was going to ask about, you've got this like time reversing identification.
Yes.
This is, should I be worried about that? Oh, well, I am worried about that.
Yeah.
Can you make me feel better about it?
Yeah. So I have sorry, I didn't explain anything about it. Let me let you feel better. So I'm doing a I'm doing a Z2 quotient on the time direction. The whole manifold here is not time orientable, but there's no closed causal curve in this geometry. It's not trivial to check that, but like there's no closed causal curve in this geometry. Does that give you better?
Perhaps.
Yeah.
But like, if I was doing some path integral or something on this geometry, then do you think the time orientation tells me whether I should weight it by e to the plus IAS or e to the minus IAS?
Yeah.
If it's not time orientable, then does everything work out anyway?
Oh yeah, probably I will discuss that at the very end of this. Yeah. So far it's just a classical geometry, and that classical geometry is like good in the sense that there's no closed time curve. So that's so far so good. But yeah, we'll discuss that later.
I have a question.
Yeah, sure.
I think you might have mentioned this earlier, but is there not an option to, instead of doing identifications in the time direction, to have the final state or the initial state have some sort of association with the two points? This path integral picture, if I didn't want to do the identifications in the timeline direction to avoid this possible problem of having to check for closed timeline curves, can I not make the boundary conditions at, say, the end slice something that would identify, like basically adding a crosscap at the final state, for example?
Oh yeah, so maybe let me draw a picture. So the kind of Z2 identification idea is that if I just like draw down a fundamental domain of the whole cell. It's something like this. So this is the global Zixia 2. And after the decompositions, it turns out to be something like this, where you just have a half of the Zixia 2, and there is a crosscap at the very center here. But answer your question.
So I guess the advantage of like looking at the picture this way as opposed to looking at the left picture and identifying points this way is you don't have to worry about identifying points at different times. Is that my understanding that correctly? Is that correct?
Oh yeah. So I mean, if you just look at this,
yeah.
then it seems to be okay that there's no need to worry about that.
Yeah.
But if you look at if you want to associate like a time-like vector field globally, like this space-time, then you will find that you cannot consistently do that. So it's like not time-oriented. Yeah. So I will go back to John's question. There should be a signature on the boundary side, and let me explain what that signature is. So at like t equal to power 2, the end of Warburg hits the boundary. And I have explained that at that point, the whole thing should be described by a time-evolved crosscap state and a time-evolved ground state. So here, I use B to denote this time-evolved crosscap state. Because if you look at this constraint, you will find that this B is nothing but actually a conformal boundary state, which appears in BCFT. So there's a very special feature of a conformal boundary state, which is a conformal boundary state does not include any spatial entanglement in it. Which means that if you look at the spatial bipartition of the boundary state, the entanglement is just 0 at leading on. Now, what we're looking at is a combination between a 0 entanglement state and a ground state. Then, okay, sure.
I thought the boundary states have infinite energy.
It has, yes.
You're Lorentz signature and a pi half you have a state of infinite energy. So I would have thought that implies that the state at any time has infinite energy.
That's a point. So if you would like to compute this, this, where T is the energy tensor sandwiched by 2 boundary states, then you will get like something goes to infinity. But what I'm actually doing here is that if you insert a T on this path integral, then you're actually looking at T sandwiched by a boundary state and a ground state. Yeah, and this is not divergent, this is like finite. Which avoids like the apparent divergence in this case.
So then I guess it's very confused by the integral structure, because I would have thought that what you were saying is that at pi half,
yes,
your CFT is in a boundary state.
No, so at T equal to pi over 2, my CFT is described by a matrix, which is a combination between a boundary state and a CFT ground state. It's not literally a boundary state, it's a weird combination between a boundary state and a ground state. Now I'm saying this boundary state has no entanglement. This has no entanglement. So
there's no entanglement for what separation?
For any separation.
It's basically a product state. It's a continuity of a product state.
I mean, if you take an interval far from the boundary, doesn't it just look like a CFT?
What do you mean by far from
the wall.
Oh, yeah, sorry.
So the boundary is in time. You're at 0 time.
Yeah, so the boundary critique is talking about is that we have time direction here, and you have a boundary like this. So the boundary state I'm talking about is that you have time direction like here, and you use a boundary to prepare a state. It's a different interpretation of a boundary. Okay, so now I've explained that this boundary state does not have spatial entanglement, and this pi/2 time slice is actually just given by a trivial slice, which is just void. Like there's no RT inside that. So whatever RT you compute on this pi/2 is actually just 0. And those RT actually does not compute entanglement entropy because our bra and cat are in different states. Instead, they're actually computing what we call a pseudo entropy. You can also show that the pseudo entropy is also 0 once you have like no entanglement state on the one side. So it's like precisely match that no entanglement structure on this pi/2. That's the signature on the boundary. I hope that answered Jeff's question. Okay, so let us try to interpret like what is the boundary dual of this DS2 group.
So in the statement that the crosscap state evolved for pi/2 is a boundary state, that's just a well-known statement in any CFT. Is there an obvious way to see it from the CFT side?
On the CFT side, it's just like you. Sorry. Okay, so let me go slightly back. So this is a constraint satisfied by a crosscap state.
Yeah.
And after doing time evolution, the time evoked operator is just written in terms of L0 and L0 bar, and just compute that commutator, you will get like this. So it's a boundary state like in this sense, but this state does not necessarily satisfy open-close duality. So it's not like a nice boundary state, but it's like sufficient to that it does not have a spatial entanglement.
No, it's not like it's not some local boundary condition.
Yeah, it's not some local boundary condition, but yeah. It can be written like in terms of linear combination of Ishibashi state.
I see.
Yeah.
Okay.
Okay, let us try to interpret the whole setup as a post selection. So as we explained, for each time slice, like the quantity we compute on the time slice is given by something like this. It's sandwiched by a different bra and cat. So this kind of thing is actually called a weak value, and it may look unphysical, but it's actually measurable using post-selection experiments.
So can I just ask another stupid question? So just if I take a free scalar field,
Yes.
what is the crosscap state? Is there any sort of like some boundary condition, some relationship between the phi's and different points or something? What?
Yeah. I will actually give an explicit example later.
Okay.
But here I just want to interpret this as a weak value. So everything you compute like in this gravitation pattern is actually a weak value on the CFT side, which can be realized by doing a post-selection experiment. So from that point of view, this DS quotient by Z2 Tensor is described by a unitary time evolution of the crosscap state, and then you use the ground state of the CFT to do a post-selection experiment. Then you can get like whatever you measure using this gravitation pattern. So in that sense, the whole like the boundary theory describing this whole setup is a unitary and local, and it has a canonical time direction. Okay, so here I would like to give an explicit example of what a crosscap state is, and comment on a relation between such an example and type 2 one-for-one algebra. So in spin system, actually we can explicitly construct a crosscap state. So what we do in that spin system is that let's say think about the spin system, which is aligned on a circle. Then you can prepare a state where you make an EP up here between the antipodal points. and you take the tensor product of all those EPR pairs. Then you can show that in some specific theories which describe critical spin chains, this is actually like a Crosscap state. So if you look at this, then now I can answer John's question. So if you look at this, if you use a if you use your Hamiltonian to time label this as the initial state, then the EPR pair will move, right? Like you, sorry. So here, like as the initial state, you have like EPR pair between this point and this point, and then if you do a time evolution, then this EPR pair will move towards each other. So this will move on this direction, and that will move on this direction. It was actually in both directions, but like they will move. Then enter the whole length is 2 pi. So what happens if you evolve by pi over 2 is that this point will be moved to this point, and that point will be moved also to this point. So initially you have a very large entanglement, but after these two EPR pairs move to the same point, you don't have spatial entanglement anymore. It's something like that. So initially you have very antipodally arranged entanglements, and after every time evolution they move towards each other, and then they move to like very near to each other, and then there's no spatial entanglement anymore. That's from this spin picture. That's how this pi over 2 comes from. Okay, but then let's just look at this state, or as a state in the spin system, and then let's just take the spin number n goes to infinity. Then the state can just be regarded as the separating vector used to construct a type 2 one-dimensional algebra. So the type 2 one-dimensional algebra in this case is supported on exactly half of the whole system. And it has been argued that the type 2 one-dimensional algebra is some algebra associated to the zeta static patch. What turns out to be interesting is that if you focus on exactly half of the whole system and then take the entanglement wedge in the bulk, then that entanglement wedge is actually exactly the static patch of the zeta 2. I'm not claiming anything by this thing, but I'm just making that as an observation. Okay. Well, maybe let me make a summary of what I have said. So what we did is that we proposed a bottom-up model which makes a connection between two-dimensional Crosscap CFT and ADS3 Einstein gravity with the zeta 2 and delta over. So in order to establish this correspondence, we computed the RB2 partition function, one-point function, current bottle partition function, and saw they match each other in a very good sense. So in this correspondence, the global the zeta 2 quotient by Z2 and of Lorentz is described by unitary time evolution of the Crosscap state, like in the CFT, and then use the ground state to post-select that Crosscap state. Then you can get whatever you compute using this replication pattern. Any questions so far? Okay, then I'll go into some discussion on future directions. So there are like several different future directions. The first one is something related to ds over Z2. So actually, this Z2 quotient is very essential in our setup. Without this Z2 quotient, we couldn't have ever found a CFT dual for the zeta and delta. Well, actually, the same Z2 quotient also appears in a version of the zeta double SYK duality. So if you look at Hermann Berlin's version of ds double SYK, if you want to reproduce the correlator the compute is, you essentially need the Z2 quotient introduced in the same way. So that's That seems to tell us maybe ds over Z2 is some good spacetime to start with. Maybe we should do something more to understand this spacetime. Actually, people have did something on that. So Schrödinger in 1956 and these people in 2000s, they have started some classical property of this kind of spacetime. And just as I mentioned, this ds over Z2 is not time orientable. So it seems that it's not good as a spacetime to do something. But it turns out there's no closed causal curves, so it has a good causal structure. On the other hand, well, if we look at some science article, there's usually some arguments about why our universe cannot be orientable or something like that. But here in this case, actually, each Cauchy slice is orientable. It's on the time dimension it's not orientable, but each Cauchy slice is orientable. And it's also interesting to try to include contributions from crosscaps in the non-boundary gravitational pattern proposal. So that's something that I'm working in progress. It's also interesting to try to define Lorentzian CFT directly on this ds over Z2. This actually turns out to be more difficult than just discussing classical properties of do gravitational pattern to go, because there's a difficulty for choosing the epsilon description, prescription, just as Henry mentioned. But there are some intriguing feature of this spacetime. So actually, in this spacetime, if you think about static observer, it has causal access to almost the entire spacetime, which is very different from global density. So probably that means if you study the algebra associated to this static observer, that could be just a type 1 algebra. There's also another intriguing feature, which is that if you think about a global densita, then you can not actually define an S matrix for effective field theory defined on global densita. But turns out if you do this two quotients, you can actually define an S matrix for the static patch, and that S matrix may be interpreted as a two-point function on the ds-CFT point of view. So there might be a duality between ds-CFT and static patch holography if you take this two function. There are some other future directions from holographic point of view. So although I motivate this study from double holography, I didn't really study double holography. I just established a correspondence between ADS3 and two-dimensional CFT. However, it would be interesting to try to discuss what actually happens on this kind of equilibrium, what kind of the theta property you can extract from that double holography point of view. It would also be interesting to study top-down constructions. And also, in our case, we only have negative tension ends of equilibrium, but it would be also interesting to try to include positive tension in the theta ends of equilibrium in some other way. It might also be connected to Coleman-DeLucia vacuum decay in some sense. There are also some.
Say a bit more about that last point, how you think it connects.
How? Oh yeah, sorry. So actually, if we look at the picture, right, this picture, it's essentially a bubble decay process, where you have a bubble here, and this bubble expands, and it bounces again. So it is essentially a bubble decay in Coleman-DeLucia. Mathematically, it's essentially that, but
there's nothing.
It's more like a bubble.
It's more like a bubble, nothing. Yeah, but with a braze.
But you can imagine putting some holographic CFT on this brain, right? then that holographic CFT is presumably due to some inside ABS spacetime. And that is actually proposed, in this paper, so that this concept might be also used to study those kind of combinatorial decay. There are also some interesting points from condensed matter point of view. So I have slightly mentioned that the gravity of a time bottle at high temperature was actually a one-sided black hole, which is typical at the first place. So it will evolve in time, but it's at the first place a volume law state, and it's for any small subregion you look at it, it's just given by a very typical thing. So that actually suggests that if you think about this kind of state, which is simply Trotter transformed Crosscap state, then that might be used to simulate finite temperature physics in quantum macro system super efficiently. And actually that is. So it was actually found by some condensed matter physicists this year that you can actually use that to simulate finite temperature physics very efficiently. You can even write that state like using a matrix product state, which is very, very impressive because we usually think, oh, if you have a typical state, it's volume law, you can never use matrix product state. But in this case, because there's a very nice antipodal structure, so you can use a matrix product state to prepare that antipodal structure and then use stick Trotter to prepare like the whole stuff.
Do you get a benefit over there from just preparing a thermal field level of 2 copies of the system?
Oh yeah, it's actually so in a one-dimensional system, it's actually just polynomially faster than thermal field double. It's not so faster, but it's still better than thermal field double.
Because it's a bit like a thermal field double, except you're using the opposite, the guy who lives opposite you rather than an auxiliary system.
Yeah.
It's like half the number of qubits you need.
Yes, and also there's a slight advantage compared to thermal field double, which is if you only want to look one side of the thermal field double, it's just a conic ensemble, right? So it's a mixed state. But here it's a pure state. So like if you want to really use a pure state to simulate thermodynamics, then this is a very good choice. I've also explained that the Crosscap state describes a separately state of type 2 one-dimensional algebra if you take the thermodynamic limit. So which means that if you use the simulation method proposed like in those papers, you can add some excitations on top of this Crosscap state and do the simulation of some type 2 one-dimensional algebra-ish stuff. This is related to Stefano's question before, because if we really want to do the same computation using field theory, then what we would do is we would prepare a cat, this is a cat, right? Like a cat which is given by C, and a rod given by C, and then do something here. And this is not tractable in the field theory language because like this is not normalizable. However, if you go back to lattice, then you can do something like that. And we already have that algorithm. So it will be interesting to look at that direction. Okay, so thanks for listening. And I think I already just gone 1 hour, so I'll just stop here.
Questions?
Are there any top-down constructions of any of these things now that this is a good model?
Not yet. I hope there could be something. So I made a slight comment on. I made a slight comment here. So people actually have thought about something which is related to defining n equal 4 square mils on RP4, and then try to find the gravity dual of those kind of superyamus. But actually, they found once they want to construct the Bob dual, it turns out to be very odd, and they didn't really achieve that. But that would be a good starting point to actually do something like this.
People have done CP2 as well, which has got the same cobordism issue.
I think CP2.
It's orientable in that case, but it's...
Yeah, sorry. I'm not sure, but I think CP2 has a trivial cobordism probably. Yeah, but sorry, I'm not sure about that. Yeah, maybe I can comment. But this cobordism structure is only true for RP2, RP4, RP6, and it's very different in all dimension. So like all the arguments I made may not work in all dimension, but it will still work.
And it gets lifted if you multiply by an internal manifold as well, right?
Yeah, please.
Do you think that, okay, in the ADS BCFT literature, people generally consider positive tension brains,
Yes.
say ADS brains in ADS spacetime? Would you
Yes.
expect that this kind of construction is similar to what you need to describe a negative tension ADS brain in ADS, or this was solid for the Caesar brains?
I think actually my situation is more similar to negative tension ADS brain in ADS BCF correspondence, where the graviton does not actually localize.
Yeah. Well, what I'm asking is, do you expect like the dual of an ADS brain with negative tension in ADS to be some cross-cap construction like this, or because in your case you work with the Caesar brains?
Oh, yeah. Oh, sorry. Are you asking that once I change the tension to another sign, would the same thing still work?
Sorry?
Are you asking that if I change the tension to another sign, would the same thing still work?
No, I'm asking if you take an anti-Caesar brain with negative tension,
Oh, yeah, sure.
then would you expect to have the dual to be a cross-cap construction like this?
No.
Okay.
And the reason for that is because like they have different symmetries.
So do you have any guess what that is? Because in SPC, I don't think you can get BCFT because that would imply some negative boundary entropy, which I don't think we have a good understanding of, right?
So you want to introduce a crosscut on the ADS brain, right?
No, I'm just trying to understand if you have a guess of what a negative tension, since you managed to identify the dual for the negative tension Caesar brain.
Yeah.
If you have an idea what a negative tension anti-Caesar brain could be equal to.
I think that's still a BCFT. Like the reason why we usually don't discuss about this is because there's no localized graviton. It seems that positing from double Holographic point of view, but I think that's still BCFT.
But is there a good interpretation of negative boundary entropy for BCFT state?
Oh yeah. Actually, you can find explicit examples like in like WZW model, which has like negative.
Negative boundary.
Yeah. It's actually not strange at all.
Okay.
From CFT point of view. Yeah.
Other questions? Okay, if not, it's time to share.